Welcome to the Explainer. Okay, let's be real. If you've ever written a piece of code that you know is correct, but it still fails because of a time limit exceeded error, then this one's for you. Today, we are unlocking the secret to writing algorithms that aren't just right, but are blazingly fast. We're diving deep into time complexity.
So let's just start with that scenario, because I think every single one of us has been there. You spend hours, you craft this brilliant solution, it passes all your tests, you feel great, and then you submit it, and boom, that dreaded time limit exceeded error. So frustrating. What on earth is going wrong?
Well, that error message, it actually points to a much deeper truth in programming, especially if you're prepping for exams or interviews. Getting the right answer is just the price of admission. The real game, the real challenge, is designing an algorithm that is ruthlessly, incredibly efficient.
And here's how we're going to do it. First, we'll talk about why speed even matters. Then we'll get into how to measure it with something called Big O. We'll learn the rules, check out the different speed classes, see it all in action with a case study, and then we'll wrap up with a toolkit you can start using right away.
Okay, let's kick it off. Section 1. Why do we even care about code speed? I mean, computers are so powerful these days, right? Can't we just wait a little longer? Let the hardware do the heavy lifting? Well, as you're about to see, the answer to that is a very, very hard no.
The reason why is all about understanding this idea of time complexity. Now think of it like this. It's a way for us to predict how our code is going to perform before we even hit the run button. It's an estimate of how the runtime is going to grow as the size of our input, which we'll just call n, gets bigger and bigger. This is our secret weapon for smashing through that time limit wall.
So, if we want to predict performance, we need a way to talk about it, right? We need a language for it. How do we actually measure this rate of growth? Well, that brings us right to Section 2, where we're going to learn what I like to call the programmer's X-ray vision, Big O notation.
We use this special notation called Big O. It looks just like this, a big capital O with some stuff in parentheses. This is the industry standard for talking about an algorithm's performance. And what's so cool about it is that it lets us ignore all the little details and focus only on what really matters, how the runtime scales as the input gets huge.
And that little n you always see tucked inside the parentheses, that's super simple. It just represents the size of your input. You know, if you're working with an array of 100 items, n is 100. If you have a string with 1,000,000 characters, n is 1,000,000. It's the variable that our runtime depends on.
Okay, now for the really practical bit. How do you actually look at a piece of code and figure out its Big O? This is Section 3, the rules of complexity. Think of these as your decoder ring. They let you analyze any algorithm and see the hidden performance costs that are buried right there in the code.
Now, here's the good news. Even though code can get really complicated, its time complexity usually boils down to just three main things. We're going to focus on these building blocks: how to handle loops, what to do when you have consecutive chunks of code, which we call phases, and of course, how to deal with recursion. All right, loops, this is the big one. This is the #1 thing you need to look for. A single loop that goes through n items, that's what we call linear time, or O of n. But the second you put another loop inside that one, the work multiplies. 2 nested loops gives you O of n squared. 3 gives you O of n cubed. This is a critical pattern to spot, especially in an exam.
So what happens if your code does a few things one after the other? Like first it does a loop, and then it does a nested loop? Well, the rule here is actually really simple. You only care about the slowest part. The slowest phase is your bottleneck. It's the part that's going to dominate the runtime when n gets really big. So an O of n part followed by an O of n squared part is just O of n squared.
And then there's recursion. The trick here is to look at two things. How many new calls does each function call make, and what's the work being done in each call? If a function just calls itself once, it's usually linear, O of n. But if a function branches, calling itself twice every single time, well, that creates this massive chain reaction, an explosion of calls. That leads to exponential complexity, O of 2 to the n. And trust me, the difference between those two is absolutely gigantic.
So, by using these simple rules for loops, phases, and recursion, we can start to categorize our algorithms into different performance buckets. And that brings us to Section 4, the complexity classes. This is basically a field guide to algorithm speeds. It helps you know almost instantly if an idea you have is going to be fast enough. And here's that field guide. O1 is the absolute holy grail. It's instant no matter how big the input is. O log n is incredibly fast. This is what you get when you can cut the problem in half at every step. On and O log n are fantastic. These are your targets for most problems. Now once you get to On squared, you gotta be careful. It's okay for small inputs, but it gets slow fast. And O to the n, that is the danger zone. It becomes unusably slow almost immediately.
Okay, theory's awesome, but let's make this really concrete. It's time for our case study. We're going to apply everything we just learned to a classic programming problem, and you're going to see the absolutely dramatic, real-world difference between these complexity classes.
So here's the problem. Maximum subarray sum, pretty famous one. Imagine you get an array of numbers. Some are positive, some are negative. Your job is to find the one continuous chunk of numbers that adds up to the biggest possible sum. And we're going to look at 3 very different ways you could try to solve this.
First up, the brute force method. 3 nested loops just to check every single possible start point, end point, and add up everything in between. That's O of n cubed. Then we'll look at a slightly smarter way where we get rid of one of those loops. That gets us down to O of n squared. And finally, we'll see a truly brilliant, clever, single-loop solution called Caden's algorithm, which is a beautiful O of n.
Okay, now this slide is where it all comes together. This is where theory hits reality hard. Look, for a tiny input of 100, they all look instant, no big deal. But just watch what happens. At just 10,000 elements, our O(n) cube algorithm is already taking over 10 seconds. That's an automatic time limit exceeded fail. At 100,000, even our smarter O(n) squared algorithm is taking over 5 seconds. The slow algorithms don't just get a little bit slower, they hit a wall. And this right here, this shows you the sheer power of picking a better algorithm. Now look at algorithm 3, the n solution. Even with 1,000,000 elements, the runtime is still effectively 0. It's instant. This is the difference between a failing submission and a correct one.
So let's wrap this all up. How can you take this knowledge and use it as a practical tool to solve problems faster? Well, that's our final section, building your algorithm toolkit. Seriously, think of this next part as your cheat sheet for any exam or technical interview you've got coming up.
This table right here is your secret weapon. The problem statement in an exam or an interview always gives you constraints on the input size n. And based on that number, you can make a really good guess about what kind of time complexity they're looking for. If n can be up to 1,000,000, you know for a fact that an O of n squared solution is going to be too slow. You have to find an O of n log n or an O of n approach. This instantly narrows your focus and points you in the right direction. So let's just lock in these major ideas. This is your final checklist. Time complexity is your prediction tool. Big O is the language you use to describe it. Nested loops are your absolute #1 enemy. Always look for the slowest part of your code, that's your bottleneck. And for pretty much any problem with a large input, your target should be O of n or O of n log n. And that's our explainer on time complexity. You literally have the tools now to look at a problem, not just as a test of is it right, but as a puzzle of is it fast enough. You can see the hidden costs in every single loop, in every line of code. So the only real question left is, what are you going to build now?